Hi! Welcome to our deep dive into projectile motion. After completing this lesson, students should be able to know the main features of projectile motion, know the position of a projectile at every instant of its motion, know the velocity of a projectile at every instant of its motion. Let's start with the lesson. In this video, we're going to unravel the mysteries of how objects travel through the air after being thrown or launched. This concept is not just pivotal for your physics classes but also crucial in real-world applications like sports, engineering, and even space travel. In this video, you will find a detailed explanation of this type of motion, which is very common, as most objects thrown in the air perform a projectile motion. The first thing is to understand the meaning of a projectile. The first question that comes to our mind in this case is, what is the projectile motion? Well, basically, a projectile is nothing more but the combination of purely horizontal and purely vertical motion, determined by the effect of gravity, when an object is thrown at an angle different from 0 and 90 degrees to the horizon. If the launching angle was 90 degrees, the motion would be purely vertical, and the object would rise to a maximum height and fall down to the original position. This is represented in the figure by the two vertical vectors aside from the projectile. On the other hand, if the object is thrown horizontally, it would move only in that direction for a short time, and eventually fall on the ground due to the effect of gravity. The horizontal arrow shows this part of the projectile. When dealing with projectiles in school, you must consider the following things. If we neglect the air resistance, then gravity is the only force acting on the object. Gravity acts downwards and is constant near the Earth's surface. Studying the projectile motion is a very challenging task. To make this task easier, we divide the study of a projectile into two parts, which determine the components of this type of motion. The first component is the horizontal one. If we neglect the air resistance, this component represents a uniform motion. The vertical component is a uniformly decelerated motion when moving up and a uniformly acceleration motion when falling down. Again, we neglect the air resistance when studying this component. The value of acceleration caused by gravity is 9.81 meters per square second near the Earth's surface and is taken as constant when dealing with a projectile. The vector of such an acceleration is directed downwards since Earth pulls all objects downwards. Gravitational acceleration is denoted as lowercase g. A fundamental element when studying a projectile is to know how to measure it. For this, we need to determine a reference point, from which all calculations start. This point is known as the origin O, and usually is taken below the initial position of the object, at the ground level. The x-axis shows the horizontal component and the y-axis shows the vertical component of a projectile, as shown in the figure. Thus, after some time t, the object is, for example, at point A, which has an x and a y coordinate. The goal is to determine the x and y coordinate for a projectile t every instant t. The first thing to calculate when dealing with a projectile is, therefore, the position of the object at a given instant t. For a better comprehension of this topic, we will consider all possible scenarios of a projectile motion. Let's consider the simplest case, which deals with an object thrown from the ground, which falls again on the ground, like in this figure. The following quantities are involved in the calculations when dealing with projectiles. The initial position is represented by two coordinates, x0 and y0, because a projectile represents a two-dimensional motion, and therefore, it needs two coordinates. x0 represents the initial horizontal coordinate and y0 is the initial vertical coordinate. The final position is represented by two coordinates xt and yt. They represent the position of a projectile after a given time t from the start of motion in each direction. The position is usually measured in meters, but for long distances, we also use kilometers or miles. The moving time t from the beginning of motion. In general, time is measured in seconds for short motions and in hours for long motions. This is also true for projectiles. The fourth quantity in a projectile is the acceleration. As explained earlier, it is represented by the gravitational acceleration g, measured in meters per square second, which is taken as negative because is directed downwards, that is, opposite to the positive direction on the y-axis. Look at the figure. The fifth quantity is the initial velocity, v0. It is the velocity at which the projectile is launched. The initial velocity is also studied in components. One horizontal component v0x represents the horizontal component of the initial velocity, and v0y, which represents the vertical component of the initial velocity. The unit of initial velocity is meters per second. The sixth quantity in a projectile is the final velocity, v. It is not always final in the sense that it represents the velocity at the end of motion. Often, it represents the velocity at which the projectile moves t seconds after the start of its motion. Like in the initial velocity, the final velocity is also studied in components, one horizontal component vtx, which represents the horizontal component of the velocity at the time t, and vty, which represents the vertical component of this velocity. The unit of velocity at the time instant t is meters per second, just like for the initial velocity. Another thing to consider here is the launching angle theta. It shows the direction of the initial velocity to the horizontal axis. Thus, based on trigonometry topics, it is clear that the horizontal initial velocity v0x is written as v0 times cosine theta and the vertical initial velocity v0y is written as v0 times sine theta. Now, let's explain how to find the position in the projectile at every instant t when the initial velocity v0 and the launching angle theta are known. For this, we use two formulas, known as the equations of motion for the projectile. Their equations are: according to the x direction we have a uniform motion, so we will use the equation of uniform motion xt equals x0 plus v0x times t. When we replace v0x with v0 times cosine theta, this equation becomes xt equals x0 plus v0 times cosine theta times t. In the y direction, we have a motion with constant acceleration, so we write the corresponding formula you have seen in the vertical motion, watched our video about vertical motion. It is yt equals y0 plus v0 y times t plus g times t squared divided by 2. When expressed in terms of the angle theta, this formula becomes yt equals y0 plus v0 sin theta times t plus g times t squared divided by 2. Now, let's consider a numerical example to clarify this point. An object is launched from the ground level at 40 meters per second and at 53 degrees in the horizontal direction. Calculate a. the total time of motion until it falls again on the ground. b. the position of this object after 5 seconds of motion. Take the cosine of 53 degrees equals 0.8, and the sine of 53 degrees equals 0.6. In this example, we have the following clues. Initial velocity is 40 meters per second, time is 5 seconds, launching angle theta is 53 degrees, where the cosine of theta is 0.6 and the sine of theta is 0.8. We have to find the total time of motion, that is t total, and the position of the object after 5 seconds, that is x of 5 and y of 5. Solution. To find the total time of flight, we account for the fact that the y-coordinate of a projectile when it touches the ground is yt equals 0. So, given that the initial position x0 of this projectile is also 0, as it starts moving from the ground level, substituting the known values in the general formula of position in a projectile yields 0 equals 0 plus 40 times 0.8 times t plus minus 10 times t squared divided by 2. Here, we have taken the approximate value of 10 for gravity instead of 9.81 for easier calculations. The sign minus indicates that gravity is in the opposite direction to the positive direction of y. Doing the operations yields 0 equals 32t minus 5t square, or 5t square equals 32t. This equation is factorized as t times 32 minus 5t equals 0. The first solution is t equals 0. It represents the first time when the object has been at the ground level. We know that this occurred at the moment when the object was launched, so we are not interested in this value, but we found it for the calculation's sake. The first solution is obtained by solving the equation 32 minus 5t equals 0. The value is t2 equals 6.4 seconds. It represents the time when the object has reached the ground level after the flight, so this is the value that interests us. Therefore, with the approximation used for gravity, we found that the object falls on the ground after about 6.4 seconds, but the true value is approximately 6.51 seconds. To find the position of the object after 5 seconds of motion, we simply substitute t equals 5 seconds in the equations of motion for each direction. The object will be somewhere at point A, as shown in the figure. Thus, the horizontal position xt after 5 seconds is xt equals x0 plus v0 x times t, that is xt equals x0 plus v0 times the cosine of theta times t. We know that the initial horizontal position x0 is 0, so, substituting the known values, yields x5 equals 0 plus 40 times cosine of 53 degrees times 5. This gives x5 equals 40 times 0.6 times 5 equals 120 meters. This is the horizontal position of the object after 5 seconds of flight, that is, the x-coordinate of point A in the figure. To find the y-coordinate of the projectile after 5 seconds of motion, we use the equation of motion for the y direction. Here it is. Substituting the known values obtained from the clues, yields y5 equals 0 plus 40 times 0.8 times 5 plus minus 10 times 5 squared divided by 2. This gives y5 equal 35 meters if we take gravity minus 10 and 37.4 meters if gravity is taken minus 9.81. Therefore, the coordinates of point A where the object is after 5 seconds of motion are 120 meters on the right and of the starting point and 35 meters above it. Look at the figure for a better comprehension. The following animation also helps understand the whole situation involving this projectile motion. Here it is. The entire motion of the given projectile is shown in slow motion to make every change clearer. Look at how the object changes its position at every instant. It rises to a maximum point, then starts to fall down. You can see that after 5 seconds the object has the coordinates we found earlier and the whole process lasts 6.51 seconds, a value which corresponds to our solution. In summary, in this first video about projectile motion, we explained the basics of a projectile and made an introduction to the position of the projectile when it is launched from the ground level. In the next video, we will see other, more complicated cases, involving the position of a projectile during its flight. Hope you enjoyed this video and see you in the next one.